Hello and welcome to Today I Learned Climate. I'm your host, Laur Hesse Fisher of the MIT Environmental Solutions Initiative. We've had people ask us, okay, if climate change is caused by adding too much CO2 to the atmosphere, can't we just suck it back out? Won't that solve our climate change problem? To answer this question, we spoke with someone who would know.
My name is Niall. I'm a professor at Imperial College London, and I've been working for carbon management for about 15 years, particularly recently with a focus on greenhouse gas removal or taking CO2 out of the atmosphere.
Professor McDowell shared with us that this is actually a pretty tricky thing to do at a large scale. And to understand why, well, think about the sky. Maybe you can even see it right now. Take a look. That's our atmosphere. And even though you can't see them, there is a whole mix of gases swirling around up there. Nitrogen, oxygen, argon, water vapor, and CO2 is just one of them. So Professor McDowell asked us to imagine that each molecule of CO2 in the atmosphere is a red marble, and every other molecule is a blue marble.
If you imagine a bucket of marbles, and if we have 100 marbles, and all of the marbles are red, and you're given the task of getting 5 red marbles, it's very easy. You just grab 5 red marbles. There's no work to do. If we imagine now the atmosphere, the air, it's not 100 marbles, it's 1,000,000 marbles. And of this 1,000,000, only about 400 of them are red, and everything else is blue. So you can spend a lot of energy, you will have to do a lot of work to search through all the blue marbles to find the red marbles. For every 1,000,000 tons of CO2 that you want to recover from the atmosphere, you'll have to physically move between 5 and 7 billion, tons of air. And a ton of air is as heavy as a ton of, rock, right? So it's a big effort.
Wow, so is this really possible?
Yeah, for sure. It's technically eminently feasible. As we've discussed, it requires a lot of energy. It takes a lot of work to sort through all of the atmospheric marbles to find the carbon, but you can totally do it.
And in fact, people are doing it, or at least trying it out. The technology is called DAC, direct air capture, because you're capturing CO2 directly out of the air. There's a company with 3 facilities in Europe, there's a different company with one up in Canada, and there's an oil company testing it out in Texas.
Every time I turn around, there's news of somebody else, proposing a DAC pilot. Pilots can come in many shapes and sizes.
So if I were to tour the facility, what would it look like?
When this has been trialed in different places, you're talking about a bank of units, a bit like shipping containers. So say, 2 meters by 2 meters, this kind of thing. And that has a big fan on it. And that fan is sucking air through. And it's just sucking the air through and blowing it over some kind of contactor, which will react with the CO2. And that's directly pulling the carbon out of the atmosphere.
What is the contactor? Is that a chemical solution of some kind?
Yeah, so very simply, CO2 is an acid. So whatever you want it to react with will want to be some kind of base or a caustic or an alkali material.
Okay, so you have this chemical solution that acts like a sponge, pulling out the CO2 from the air. But then you gotta wring the sponge and get the CO2 out.
So you do that simply by adding energy. So if it's in the liquid form, you have to effectively boil it down. And this allows you to recover a pure stream of CO2, which you can compress, transport, and store.
Once you have all of this extracted CO2, you gotta put it somewhere where it won't go back up into the atmosphere.
So this is typically underground. In Texas, for example, people are talking about having direct air capture technologies to directly transport the CO2 into oil fields that are very nearby.
If you want to know more about storing CO2 underground or using it to produce other things like building materials, check out our episode 7 from season 2 on carbon capture, which is about capturing the CO2 out of the smokestacks of manufacturing and power plants. But shipping containers with big fans isn't the only idea we have to take CO2 out of the atmosphere.
So the important thing about greenhouse gas removal or carbon dioxide removal is that it's a portfolio of different approaches. some of which rely on engineered technologies. So this is direct air capture or some forms of what's known as enhanced weathering. So that's reacting CO2 with crushed rock, or bioenergy with carbon capture and storage pathways. So that could be turning biomass into heat, power, mobility, and then you capture whatever CO2 you can. There are ways in which we can improve and change the management of our natural environment. So one good example of that, one really important example of that is afforestation. So turning a landscape into a forested carbon sink, and similarly changing the way in which we manage peatlands, wetland restoration.
Put a pin in that last one. In our next episode, we'll talk all about using forests to take CO2 out of the atmosphere. Okay, let's back up. The bottom line is that it really is possible to take CO2 out of the air. And that's sort of an intoxicating thought. Because if there's one thing we've seen on this show, it's that stopping our CO2 emissions, which Professor McDowell is going to call mitigating climate change, requires us to change the way that we get energy, the way we build, the way we travel, the way we grow food. So is carbon removal the easier way out of climate change?
In my personal opinion, no. Greenhouse gas removal through any pathway, whether it's direct air capture, bioenergy CCS, afforestation, or any other option, it is not an alternative to mitigation.
Why is that?
Very simply, most mitigation will be cheaper, just simply more cost effective than greenhouse gas removal. We are at, I think, very early days of developing direct air capture technology. You know, the basic science is sort of there, right? We know how to capture the CO2. The problem is that what we need to do is be actively removing lots of CO2 at the 1 million tons per year scale minimum. An analogy, I think, is that it's a bit maybe like saying we need to be able to break the sound barrier, and Orville and Wilbur Wright have just managed to get their first plane flying for 10 meters or whatever it was. You know, that's sort of where we are. So it's far too early to rule anything out, but putting all your faith in the manifestation of some kind of technical unicorn which will very, very cheaply reverse the impact of climate change, I think is brave, and I wouldn't do it.
And this is the central challenge with carbon removal. If you look at it as an economist would, like how much it costs to remove or avoid a ton of CO2, direct air capture isn't yet cheaper than pretty much any other option. Building wind and solar, even capturing and storing CO2 from smokestacks is cheaper. So, if it's so expensive to take CO2 out of the atmosphere and so much cheaper to avoid putting it there in the first place, then why invest in CO2 removal at all? Well, it's because a lot of CO2 has already accumulated in the atmosphere. And that CO2 is going to be warming the Earth for a long time. So we will need to remove it if we're going to keep global warming in check. In fact, almost every scenario that scientists have come up with for how to keep global warming at relatively safe levels has large-scale carbon removal by the end of this century as one of the key tools in our toolkit.
We have to mitigate as fast as we can with every tool in our arsenal, and we will also very likely have to think about greenhouse gas removal options as well. We will need everything. We need renewable energy, we need fuel switching, we need nuclear power, we need demand reduction, we need carbon capture and storage, and we will need all forms of greenhouse gas removal as and when they get going.
We're going to stay on this subject for our next episode and talk about another way to absorb that CO2 using trees and nature. But for now, I want to thank Professor McDowell for joining us and remind you that you can always check out our website, tilclimate.mit.edu, or our Twitter @tilclimate for a bunch of resources that we've pulled together. We got fun facts and other websites, our sources, and educator guides so that teachers can use this podcast to introduce climate change in the classroom. As always, email us your questions at tilclimate@mit.edu, and thanks for listening.